Good afternoon, all. First, words to the organizers, of course. This is the first time with some of my students. This is a great initiative. In fact, the first to congratulate is Volkan Hoca, probably, but all the team, and also it's a really professional organization. I mean, it's not an amateurish type thing. Then once again, this is a great thing. And I think indeed that it's very good also for the students. You know, they probably first of a kind experience of presentation in English and answering to the questions, etc. But this is really great for them and for everybody. Well, concerning the the topic of this session, indeed we shall talk mostly technology. In the first two sessions, it was also technology, but the first session was, in fact, mostly on the operationalisation. It's easier to say in French, of existing technologies, rooftop, things like that. The second session, mostly legal and policy issues, very much important, of course. All the structures, infrastructures or superstructures adapt or try to adapt to this newcomer. And now we start to discuss indeed mostly technology. Well, hydrogen is part of that, but of course not only. Then we have a good panel of which is in fact very much important. You know, if in terms of Turkey, in terms of everybody, but for Turkey, we have a kind of lack or gap, as you know, in technology development, authentic or local, as we say now, yerli and milli technology. So perhaps this time we should be a little much more quicker to adapt, to respond to this technology challenge. Not only technology, but in fact, well, hydrogen is a good thing, but as Volkan Hoca mentioned, we have to produce it. So one technology is to generate this hydrogen in a clean way, of course. So technology is everywhere, and to use hydrogen needs also technology. To use or to generate other renewables or decarbonized fuels and whatever, we need technology. So then universities and R&D systems and of both of industry and TÜBİTAK, that we have a good challenging situation. Then we shall try to answer partly today. So Ahmet Hoca, you would like to add something?
I mean, this is a great introduction. I mean, nothing to add. I think we can proceed to presentation now. So first presenter will be Muiz Adekunle. If you like, we can start with him. Muiz, you can introduce yourself and start your presentation, maybe.
Okay, thank you. Sorry, I was on mute. I am Muiz Adekunle Agbaje from Department of Mechanical Engineering, Yıldız Technical University, Istanbul. I will be talking, as I said, I'm from Department of Mechanical Engineering at Yıldız Technical University here in Istanbul. I'll be talking on the energy systems of the future with specific reference to bidirectional energy systems. In this presentation, I'll be talking on the future of energy. I'll be giving an insight on bidirectional energy systems. I'll be talking on the reversible solid oxide cell system as an example of a bidirectional energy system, the applications of this system, the aspects of the thermodynamic and economic analysis of the reversible solid oxide cell system, some demonstrations that have been made and used, and some researches that has been done in terms of reversible solid oxide cell systems, the benefits of the system, and finally, I'll conclude on this discussion. So when we talk about future energy systems, we are talking about systems that are characterized by so many things that we want as part of our energy in the future, how we want energy to look like in the future, the energy ecosystem, what do we want it to look like? We talk about demand side management, we talk of net zero energy systems, we talk of renewable energy systems, solar, wind, and light. We talk of increased energy efficiency. We talk about the green energy in terms of CO2 emission reduction. We talk of so many things that characterize these systems, and these characteristics will result in systems with high integrity, systems that have high security of supply, less expensive systems, and the like. A future examples, I mean types of these systems, we would have hybrid systems that would have more than one energy generation system. For example, we could have a conventional coal power system with a geothermal system. We could have something like we could have an energy generation and storage system. We'll talk of smart grid systems. We talked about the global energy grid, where we have the whole world on one power grid. We talk of feed-in tariffs, where power generation are carried out by citizens of the country and supplied to the national grid and sold to the government. We talk of green buildings, for example, the building integrated photovoltaic systems. We talk of the microgrid, we talk of zero energy buildings, among others. These are part of the systems we expect to see as future energy systems. Now, talking about hybrid energy systems, an example of the hybrid system is the bidirectional energy systems that I will be talking about here today. A bidirectional system is a system that serves for both energy storage and energy generation. I should note here that bidirectional energy system is a system that it has to be one system that will function both as a storage system and generation system as a whole, not a storage system that has generation incorporated to it. That is not a bidirectional system. So these systems are characterized by power to X or X to power. Here, X here could be hydrogen, could be heat, depending on how the system is configured. An example of this system is the reversible solid oxide cell system that I will be talking about here today. A reversible solid oxide cell system is an electrochemical cell system that functions as a fuel cell for electricity or power generation and as an electrolyzer cell for energy storage. This system, of course, since being a system, it has to contain at least two components. So for reversible solid oxide cell system, the system have other components such as the heat exchangers, we have the heaters, we have the compressors, turbines. Depending on how the system is configured and the size of the system, these components, we call them the balance of plant components. They are used to set the temperature and pressure of the gas, the exhaust and the flow gases in the system to set the system performance and system characteristics. So these systems could be applied for heat stabilization. They could be used purely for energy storage. They could be used for hydrogen production when the system works with steam. They could be used for carbon utilization, where they could be used to generate synthetic natural gas, or they could be used to store electricity in form of syngas. And also they could be used for heat generation, because reversible solid oxide cell system or solid oxide cell system in general, they work at very high temperature, at temperatures above 500 degrees centigrade up to 1000 degrees centigrade. So the aspect of heat generation, thermal management, among others, in the system. So in the aspect of the thermodynamic analysis, we talk about the heating value of hydrogen or the synthetic natural gas generated from the system when it is operating in storage mode. We talk about the power generation or heat generation and consumption in the system. We talk about the round trip efficiency of the system, which is the ratio of the power generated to the power stored in the system. We talk about the storage size, where this is usually the size of the tank used for storing the fuel, probably the hydrogen or the natural gas, depending on the fuel used in the system. We talk about the fuel utilization of the system, because it is, I will explain that as we go further. It's a system that works on cell stacks. So the amount of force supplied to the system is not usually the total consumed, just like we have in chemical reactions. So the fuel utilization ratio is actually very important in thermodynamic analysis of the system. We talk about the cell degradation rate per cycle. As I said earlier, this the system, the reversible solid oxide cell system, they work at relatively very high temperature, so which makes degradation in the cell. So the rate of degradation per cycle is also important in characterizing the cell and the system as a whole to determine the lifetime, the efficiency, among others. Also the active cell area, the current and power density, which is the ratio of the current or the power in the system power generated or power stored by the system to the active cell area. And of course, we have the cell voltage of each individual cell, which amounts to the total stack voltage in the reversible solid oxide cell system. In the aspect of the economic analysis, we talk of the capital cost associated with the stack of the system, because in the system, as I mentioned earlier, the other balance of plant components are actually mature technologies. The prices could be predicted or probably asked from vendors during the economic analysis. However, the capital cost of the stack is not, there isn't enough data to predict the cost of the stack. So the capital cost of the stack is very important, as it takes a large amount of the total cost of the system. The cost of producing hydrogen or the synthetic natural gas, depending on the operating fuel of the system. When I talk about operating fuel here, I'm talking of either steam or carbonaceous gases such as carbon dioxide or the like, depending on how we choose to operate the system. And the cost of producing these gases is also important in the economic analysis of the system, because we have to achieve a beneficial cost of producing this hydrogen or syngas. Otherwise, no matter how efficient the system is, if the cost of producing this gas is not competitive with what is available in the market, it's just another waste of technology. Also, the levelized cost of electricity generation. So the cost of hydrogen and synthetic natural gas is during the storage mode of the system. That's when we talk about hydrogen production or synthetic natural gas production. Now, during the generation mode of the system, electricity is generated. Levelized cost of generating this electricity is very important, because if we do not take cognizance of this cost of electricity generated, it could be, if it is not in par with what is available with other types of systems, such as the pumped hydroelectricity system and the like. If it is higher than those systems, it is just as good as not having a system, because nobody would want to pay more for a system, no matter how good or how interesting it seems. So now going to the system as a whole, the demonstrations that have been carried out, we've had experimental demonstrations and of course the computational modeling of these systems. For methane synthesis for grid stabilization was carried out for a 2 megawatt by 1 megawatt system, and the system was simulated computationally, of course, and it had a round trip efficiency of 70%. An experimental demonstration, I will explain, I'll go further on this in the next slide. This one had an efficiency in the electrolysis mode. SOE here means solid oxide electrolysis cell. It had a 71% storage efficiency and 41% power generation efficiency. This was integrated into actually a utility, a grid for grid energy storage, and it worked perfectly well with the grid and at 120 kilowatts and 50 kilowatt hour rating. Also, a study was carried out earlier this year for 50 megawatt system for integration into natural gas pipeline for carbon utilization and for grid energy management. And a very high efficiency was demonstrated compared to every other system here in terms of the generation efficiency. It had also efficiency of 69%, and the electricity efficiency was 84%. Also, this self-feasibility study was carried out earlier to show the feasibility of operating a fuel cell in both as an electricity cell and as a fuel cell. The reversible, practically the reversible operation of the solid oxide cell system and a solid oxide cell stack in this situation. It's a stack, not the whole system, just a stack. A 10-cell stack was tested in this operation, and it showed a very good performance in terms of both as the fuel cell and as the electrolysis cell. As I said earlier, this 120 kilowatt by 50 kilowatt system that was incorporated into a grid is explained here. We have the solid oxide cell stack here, and then the wind electricity was generated from solar, wind, and the grid, and they were supplied to this stack where it has the hydrogen storage, it has hydrogen compression system, it has the desalinizer, the ionizer unit for the water that was used, because water was used here to generate hydrogen. And this is the whole system, which it showed a very good efficiency, as I explained earlier. So further research for anyone that could be interested, I selected these two researches because they showed they are very detailed in terms of the work that was done. This 2015 study.
Muiz,
Yes, sir.
You have 3 minutes left.
Of course, I have just 2 slides left.
3.
Yes, this design study was carried out this design was carried out for the engineering design of the reversible solid oxide cell, the performance analysis of the operating condition selection, among others. This 2015 study. 2017 study showed the feasibility of this with respect to spot electricity and fuel market for a 2015 target of Denmark. And this 2019 study showed the integration of this solid oxide cell system into the natural gas pipeline of Alberta in Canada. The benefit of this system, as I said, it's a one system that functions as 2. So there is up to almost half capital cost reduction to be used for grid frequency regulation, peak demand shaving, and load shifting services. They could be used to generate hydrogen for transport fuel, and of course, power to gas application. So this is just to show this figure is from IRENA in 2018 to show a hydrogen economy. This shows us how reversible or solid oxide cell system can be integrated in an hydrogen economy where electricity is converted to hydrogen and used in different applications, as you can see in the picture. And in conclusion, I'd like to say that the reversible solid oxide cell system as a bidirectional energy system is an essential part of the future energy system for large and medium scale energy applications. It can be used also for carbon dioxide emissions reduction, for energy system balancing and energy security, and also in an hydrogen economy. Thank you for listening.
Burning questions, if there are. No? Well, I can ask one if you want. Muiz, so this is what? This is your master thesis?
Yes.
And then how it will progress? Will you have a kind of small experimental setup, or will you do some simulations, or for the moment it's just
well,
a temperature survey?
Due to cost restrictions, I will just be doing a simulation. Actually, I have the system that I've already designed and simulated. I have it already. So I'm presently carrying out economic analysis on the system.
So it will be essentially kind of simulation.
Yes.
Okay. Any other questions?
Muiz, let me ask this. Have you made any search about the capital cost of building this structure and operational cost? Because that are also important, you know.
Yes, of course. In terms of capital cost, for the reversible solid oxide cell system, presently, I am using the cost of solid oxide fuel cell because we believe that it is the same fuel cell that will be used as an electricity cell. So the same cost analysis go. We have cost, let me put it, we have history of cost of solid oxide fuel cells system, the stack just the fuel cell stack. So that is what I'm using to simulate the cost of the cell stack.
So the output methane will be fed into the natural gas pipeline?
Pipeline, yes.
So you are also calculating the benefit from the natural gas, right? Because
Yes.
you are selling. So your simulation will include the economic part.
Of course, definitely.
Okay, hopefully it will be good. Okay, thank you.
You're welcome.
Any other question? These solid oxide things, but you mentioned it, they work at very high pressures. So what is it? Is that correct first?
Of course, yes.
Yeah. So what are the limitations of this? I mean, the high pressure system being integrated to other systems. What are the limitations of, let's say, of integration and system-wise?
Yeah. In terms of pressure, it does not necessarily have to operate at high pressures. You could have pressures at
high temperatures, not pressure.
Okay, high temperature, of course, that is one of the major problems with the system as of now. There's a problem of thermal management in the system due to the relatively very high temperature. I'm not going too deep into thermal management of the system as a whole, but for the stack on its own, the stack are made of ceramics. We are talking of LSCM and the like. So I mentioned earlier the issue of cell degradation. This high temperature is also responsible for the cell degradation, but studies are being carried out with respect to that. However, for thermal management, the system will be cooled. The stack, of course, will not be cooled by external means, but we use excessive air because the system works on fuel and air. So we use excessive air. We run excessive air through the system to cool the system by itself, thus generating heat for either storage or any other auxiliary uses.
Okay, perhaps a last question, if there is any. If not, Ahmet Hoca, we move to the other one.
Yes, and that is I think your student, Dilay. Thank you, Muiz, for this presentation.
Thank you, Muiz. Yes, compared to the original program, we just interchanged the second and the third. Then Dilay, Güleryüz will start. You can handle the session if you want.
Okay, thank you, Hocam. I hope everyone can hear me well.
Yes, we can hear you.
Okay. Good afternoon. My name is Dilay Güleryüz. First of all, I would like to express that I'm very glad to be a part of this organization. I'm a graduate student from Middle East Technical University, Department of Mechanical Engineering. And today I'm here to present you my study on green hydrogen for Turkish glass industry. So here's the outline of the presentation. We will first talk a bit about hydrogen and hydrogen generation technologies, and then a brief introduction to the connection between glass industry and hydrogen will be made. And this will bring us to the biggest glass manufacturer of Turkey, Şişecam. Lastly, I will present the analysis and findings of green hydrogen generation potential for several Şişecam plants in Turkey. And then we will shortly conclude all of them. Now let's start. We do know hydrogen. It's in water, it's in organic substances, it's basically everywhere. And in fact, hydrogen may be the most abundant substance in the universe. Realizing its potential, Jules Verne once referred water and hydrogen as the future coal in one of his books. So if there's that much amount of hydrogen, we should be using it somewhere in the industry. In fact, hydrogen has a wide range of applications, from ammonia production, protective gas applications, and energy applications to decarbonizing carbon-intensive industries, such as iron and steel, cement, or glass. And in this presentation, we are interested in this kind of applications of hydrogen. So in order to decrease carbon dioxide emissions and start a transition to green hydrogen, hydrogen-intensive industries may be a good start. And as being said, glass industry is one of them. So in order to understand how to decarbonize a sector by hydrogen, let us first cover hydrogen generation technologies. These techniques can be divided into three by using a simple color code and based on their carbon dioxide emissions. Firstly, gray hydrogen. And gray hydrogen refers to hydrogen generation from fossil fuels. Oil, coal, or commonly natural gas can be used as the source in this kind of applications. The costs are low, and in fact, it's the cheapest way to produce hydrogen. However, carbon dioxide emissions are very high. The second one is blue hydrogen. Blue hydrogen is an interesting concept. Here again, fossil fuels are used as source, but a carbon capture and storage technology is implemented into the system to reduce the carbon dioxide emissions. And this technique is not very popular considering the costs of carbon capture and storage technologies and the taxes. And lastly, green hydrogen comes, and in these applications, decarbonized electricity is fed into a water electrolyzer to produce hydrogen. The decarbonized electricity comes from renewable sources, such as wind, solar, or hydroelectricity, or other renewable sources that you can imagine. The costs of using renewable sources decrease every day by developing technologies, and therefore water electrolyzers are gaining more attention. The electrolyzers can be alkaline or polymer electrolyte membrane, namely as PEM electrolyzers. PEM electrolyzers are quicker to respond to changing electricity. Therefore, they are preferable with renewable energy sources. However, their costs are higher than alkaline electrolyzers. Now we will briefly talk about the role of hydrogen in glass industry. Hydrogen is employed in flat glass production, and here you see a production line of float glass. The raw mixture consisting of quartz sand, dolomites, soda, and lime is melted and floated into a tin bath. And in the tin bath, the glass takes its flat and flawless form. The atmosphere of the tin bath is very important here. Because any oxygen that may leak into the mixture can create flows, and it's really unwanted in flat glass. That's why the tin bath's atmosphere is filled with 10% hydrogen and 90% nitrogen, creating an inert atmosphere. And after that, the mixture is left to cool down here and cut into sheets to take its final form. Today, float glass manufacturers use about 86 normal meter cube hydrogen and 765 normal meter cube per hour of nitrogen. The numbers are very high on an annual basis, so this makes the glass industry a very good candidate for transition to green hydrogen. Now that we know the connection between hydrogen and float glass, we can talk about the situation in Turkey. The production capacity of Turkish glass industry is about 3.5 million tons per year. And Turkey's biggest glass manufacturer is Şişecam. The company is also the 5th biggest flat glass producer in Europe. We are interested in this presentation for the flat glass. Şişecam has 4 different flat glass factories in Turkey. These are Trakya, Düzcemin, Kırklareli, Mersin, Bursa, and Ankara. And on the table, you can see the hydrogen consumed in flat glass application on each production plant. It should be noted that this hydrogen is gray hydrogen, mainly coming from natural gas. And in this study, we performed a preliminary analysis of renewable energy usage for replacing this gray hydrogen with green hydrogen in these plants. A trend analysis is performed for each location on annual basis. The hourly weather data for each location is collected and employed in the simulations. Therefore, the simulations are made for 8,760 hours to account for 1 year. The calculations are based on the given assumptions. The installed capacity of PV modules, photovoltaic modules, and wind turbines are fixed to 2 megawatt because of homogeneity in the calculations to make it easier to compare between photovoltaic panels and wind turbines to decide which one is better. And the electrolyzer used in the simulations is a PEM electrolyzer. The reason of this choice is the suitability of PEM electrolyzers to the intermittent nature of the renewable sources. The electrolyzer has 55.25 kilowatt hour per kilogram of hydrogen of power consumption. And here you see the wind turbine and solar analysis, each of 2 megawatt installed capacity for Istanbul. Istanbul is chosen to account for Kırklareli plant because the locations are very close to each other and they have similar weather characteristics. Therefore, it provides a good insight for the Kırklareli factory. The mean wind velocity in Istanbul is about 7 meters per second. Therefore, a large amount of electricity is expected to be produced from wind sources. The result is compatible with that, as you can see here. On the graphs, you can see the wind turbine power on an hourly basis. This first graph shows the annual wind turbine power generated for 8,760 hours, corresponding to 1 year. And please note the intermittent nature of the wind sources. And the second graph shows the hydrogen generation of the electrolyzers. This is compatible with the wind power graph. Coming to solar resources, Istanbul has poor solar resources, and we can see that in the results. The solar power is almost half of the wind electricity generated, and therefore the hydrogen production is like that. Coming to the pie charts, the upper pie chart shows the seasonal variation of wind electricity generation, and it's expected it is the highest in winter. The lower pie chart again shows the seasonal variation of solar power, and it is, as expected, the highest in summer. Mersin is an interesting location about renewable power potential. The mean wind velocity is from 4 meters per second to 6 meters per second. Therefore, less wind power is expected in Mersin than Istanbul. However, the solar power potential of Mersin is the highest of Turkey. And comparing the electricity generated from wind turbine and photovoltaic panels, we see that they are very close. And moreover, for the same installed capacity of 2 megawatts, PV panels generate more electricity than wind turbines. And the graphs shows clearly the intermittent nature of the renewable sources. And looking at the top pie chart, we can see that the highest amount of electricity generated from wind turbines is in winter, again, and it is the highest in spring and summer for PV panels, as expected for Mersin. Bursa, by its geographical location, performs weaker than other locations in terms of renewable sources. The province has about 3 meters per second mean velocity. Also, it has low solar power potential, as in Istanbul. However, these solar panels perform better than wind turbines in Bursa, as in Mersin. The solar power is nearly the same as Istanbul. This is expected considering the locations of the two cities. They are very close to each other. And although the amount of hydrogen generated from wind turbines is small, we can still generate a significant amount of hydrogen from solar resources in Bursa. And lastly, Ankara. Although Ankara is considered as a cold city, the mean wind velocity is only about 4 to 5 meters per second in Ankara. Therefore, it does not perform as good as Istanbul when it comes to wind electricity. However, Ankara has an interestingly high solar power capacity thanks to its location being closer to the southern parts of the country. And we can see that potential in the results. The amount of yearly hydrogen generated from PV panels is more than twice of the wind turbine generators in Ankara. Here's a summary of comparisons of the electricity generated from two different renewable sources with equal installed capacity. We can observe that the highest amount of electricity generated from wind sources is in Kırklareli, and it is the highest for solar resources in Mersin, as expected. And for comparison, the amount of consumed hydrogen is presented for each plant. The highest consumption is in Kırklareli factory, and we can meet this demand by using only 3 wind turbine generators of 2 megawatt power. The second highest consumer is Mersin plant, as you can see here. The demand can be generated by using 4 wind turbines or a relatively small PV area. Coming to Bursa, the geographic restrictions make Bursa perform weaker than other plants. However, the relatively small hydrogen demand in Bursa plant can be met with a reasonable PV area. And lastly, Ankara has the lowest hydrogen consumption, so its demand can be met with a very small PV area or by using 3 wind turbines. And as final results, it's not impossible to switch to green hydrogen in these locations for flat glass industry. And further cost analysis would provide a better insight for investments. Here are the acknowledgements. This work has been produced benefiting from TÜBİTAK's program, and we would like to express our special thanks to Professor Dr. Şener Oktik for his helps for providing us the hydrogen consumption data from Şişecam. And thank you. I'm here for questions and feedback.
Thank you.
Thank you. Ahmet, perhaps you handle the discussion?
I mean, this is great work, actually.
Thank you.
First of all, let me ask the audience, any questions, comments?
Can I ask a simple question, Dilay? You
Sure.
finish with the actual cost analysis will be soon. Are you going to do it, or someone else is prepared to do that cost analysis to convince the money to spend on those new renewables? Because the money is not easy to convince. We need a cost analysis.
Yes, hopefully we will do it.
You will do it, okay.
Yes, hopefully.
Thank you very much. I'll expect. I'm waiting for the result. Thank you.
Yeah, Ahmet Hocam.
Any other question? Let me ask.
Yeah, let me ask you another question.
Okay, welcome, Hocam.
Sure.
Yeah, I was going to ask the same question as Şener Hocam asked. You know, what kind of energy are they using now to be able to do the same work? I mean, what will be the economic benefits of this other than the environmental benefits?
We can decrease the money spent on our renewable sources when it comes to the locations that are benefitable from renewable sources than using natural gas. And really,
Are they using natural gas now for the same purpose?
yes, mainly.
Are they converting it electricity or using the heat of natural gas?
It's just reforming natural gas. If Şener Hoca, if I'm not wrong, in Kırklareli, you have your own generation system, I guess.
Okay.
Yeah.
Yes, mostly reforming generation systems, reforming the natural gas, getting the actually hydrogen out, and we use the oxygen out of that as well. Really, it's reforming technology.
Okay.
Oh, which means gray hydrogen.
Yes.
Right.
Correct.
Yeah.
And
Very
natural
good.
gas itself is not very cheap, so
Yeah, it's expensive.
yes.
Dilay, I mean, let me ask this. Already they asked about the cost, but think about it. So you are saying that, I mean, for Kırklareli, I think wind is okay. For Ankara, solar is good, better. Okay. I mean, this is in terms of the amount of energy generated and so heterogeneous. But there is also an issue of, I mean, capital cost, operational cost. So the transmission line, the market issues, the feed-in tariffs. So how do you see the future of this study in terms of the analysis to make it realistic? So
Yes.
what should be the next step?
The next step should be the cost analysis, because I believe that the renewable sources will meet its initial installation costs after a few years, and the cost analysis would prove this. And the environmental benefits are, as you know, it's very high, and I believe that it's doable.
Okay, yeah, I mean there is like, you know, hydrogen generation, and also there is some like carbon dioxide emission constraint. So you are decreasing some of the carbon dioxide. So you are like eliminating natural gas, which is expensive and a fossil fuel. So you have to include them to the model, right? And you have to build a model to decrease this cost.
Yes, we will include the installation cost, operation and maintenance costs, and the capital factors, as you mentioned. And then this will bring a more realistic scenario.
Okay, let me ask another question. So when you model the wind, there is a cut-in speed and cut-off speed. Like, I mean, so the wind turbines start to like at 5 kilometers or per hour speed and stop at 22, I think. So have you considered those constraints also, or?
Yes, the wind turbine I used has a low cut-off speed, cut-in speed to start operation. It's about 4.5 meters per second in the simulations, and therefore in these locations, the wind turbine performs well. Yes,
Okay.
and I considered that.
Okay, thank you.
Right, Hocam, probably we should say that the glass production technology is not environmentally friendly technology. there's a big pressure in Europe on the technology. Anything reducing the really carbon footsteps of this technology will help. So the glass technology, probably glass industry might look up this one quite enthusiastically. Okay. It is a good area to really do the work and just present to them. Thank you very much for working on it, Dilay.
I mean, this is a good work. Thank you for this one, Dilay.
Just one, Ahmet Hoca, final word perhaps, just to link this presentation to what Shehnaz Hoca presented this morning. Sorry. You know, this carbon border agreement business, which is in preparation in Europe, and which will be, the directive will come in the latest 2023, which will simply render impossible, prohibit the şişe cam exportations to Europe if they don't move away from gray hydrogen.
Okay.
And in the cost business, it will be costly, but the reward is very high. If not, you are out of the business. This is so serious. This is at this seriousness level of this CBAM business that we tried to introduce or discuss.
Then there is a good motivation for Şişecam to do this, I think. Okay. Thank you, Dilay. Again, we can proceed to the next one, I think. The next one is Tahsin, Berk, Kıymaz, also from Middle East Technical University, and İskender Gökalp Hoca. İskender Hocam, you want to introduce, or we can start direct? Okay, Tahsin, go ahead and introduce yourself.
Okay, hello everyone. Let me share my presentation for you first. Okay, I hope you can see the presentation and you can hear me.
Everything is okay right now.
Okay then. Hello again. I'm Tahsin Berk Kıymaz, and I'm graduate student at the Mechanical Engineering Department at Middle East Technical University under the supervision of İskender Gökalp. And today I'm going to present you the hydrogen for clean burners in Turkey. Before I can continue with my presentation, I would like to thank you for having me in this great conference. So here's my outline. First, I will start with the introduction a little bit to hydrogen energy. And after that, I will continue with implementing hydrogen energy to our everyday usage. And thus, where's the main part of my presentation is the important challenges of this hydrogen usage. And I will end my presentation with a conclusion. So why we want to use hydrogen as fuel? Because it's a carbon-free fuel, and it's really important to our path to zero carbon emission as well. And here you can see the global mechanism for hydrogen oxidation, or as we know as the combustion. And in the global mechanism, we can see that only product is the HO2, which we know as a water. So as Dilay said in the previous presentation, there are green ways to produce hydrogen, which is good. And the hydrogen can be used instead of the natural gas applications, which is really important for us since we are mostly using natural gas for applications as fuel. And the production price of the hydrogen is decreasing over the years, which is great for the future. So, but why we are not using hydrogen right now? Why we don't want to use it? Why we didn't use it as now? Because there are a lot of challenges with hydrogen. I can start with the storage. It's really risky to store the hydrogen because it's of the lightweight. It should be really pressurized if you want to store it as a gas, or we need to liquefy, but it's really costly. And also the hydrogen is really have high flammability. It's also colorless and scentless for any leakage problem, and the transportability of the hydrogen is a problem again because of the properties of the hydrogen. We need to make new pipelines, and the leakage is really problem because of the lightweight of the hydrogen. So before I continue, for now I talk about the hydrogen, but we are using natural gas in worldwide and also in Turkey as fuel. And I would like to give you some numbers about the natural gas. So according to the Gazprom report, total of 45.3 billion standard meter cube hydrogen is consumed, sorry, not hydrogen, natural gas is consumed in Turkey in 2019. And nearly all of it is imported from the foreign countries with a price of 0.25 cents dollars per standard meter cube. And the 32.6% of this natural gas is consumed in our households, which corresponds to the 14.6 billion standard meter cubes. Why did I give you these numbers? Because it cost us $3.65 billion per year just for our usage of the natural gas in our homes. So how we use this natural gas in our cooktop burners while cooking our meals, for water heaters, for get a central heating for our homes, and the gas-fired ovens usually using in the restaurants and also in some of our homes. But how, as I mentioned, we want to use hydrogen for fuel, but how can we use hydrogen in our house? Like, can we get a bottle of hydrogen or just pressurized tons in our kitchens? No, we don't want that. But how can we use hydrogen? Actually, we can use hydrogen with the existing natural gas pipelines while blending the hydrogen, some part of the hydrogen in natural gas pipelines. So this technique is great as a starting point on the way to 100% hydrogen usage in the world. And because we are using the existing infrastructure, which means that we don't need to build any other system, which means that cost. And while with using the hydrogen blend, we can decrease carbon emissions, which is really important for us, as I said. And in this figure, you can see that with the addition of the hydrogen, the carbon dioxide emissions decreasing nearly linearly. So can we do that really? Can we blend some hydrogen to our natural gas pipelines and without any problems or errors? Actually, we can do, but up to a certain point. So here's an example for you. This is a high deploy project going on in the Keele University at United Kingdom. And they are trying to use up to 20% hydrogen blend in their natural gas pipelines. And they are testing in their campus. And for now, there is no problems going on. For this project is going on for like 10 months. And they reached to 15% hydrogen blend. And for now, there is no problem. And after 8 months, and the project will be finished, and if there will be no problem, then they are starting to use hydrogen blend in the city where the Keele University is located. And this project is funded like 7 million sterling. So before I continue with the limitations of the hydrogen blending, which I talked about, I would like to briefly inform you about the burners and the flame structure. So here's a Bunsen burner. I think all of you have heard or saw it in your chemistry classes or something in your life. The gas is coming from this pipe and mixing with the air and inside the burner. And after that, with the help of the ignition, a flame occurs. And when we close up to the flame, we can see that. We can see a flame front. The flame front, you can visualize it like that. When you light up a candle or like a lighter, you see a orange structure of the flame, and you see a cone-like shape, and it's the flame front. The unburned gases coming from the burner is ignited. After that, the flame front is stabilized, and the flame front actually can be said like where the reaction happens. So the flame has a speed which wants to propagate into the unburned gases, and unburned gases have a speed that wants to lift up the flame, and the flame somehow stabilizes like this cone. So I would like to continue with the hydrogen enrichments in these burners. And before I go over that, I would like to say that there is not sufficient information and literature about domestic applications, which is our topic right now. And the safe limits should be investigated for the blending in a close-up view. And because the properties of the mixture changes with the hydrogen concentration, we need to determine these limits carefully and which property is changing. Actually, the flammability limit of the hydrogen is wider than natural gas, so the mixture's flammability limit will change. And since the hydrogen has lower ignition energy, it can be ignited much more easily. This is one of our main concerns. And the temperature will increase with the hydrogen addition, since the flame temperature of the hydrogen is much higher than natural gas, and also the flame structure changes with the hydrogen addition to the flame. So lastly, there's a phenomena called flashback, and which is really important while determining the limits of the hydrogen enrichment in the burners. From now on, I would like to continue my presentation with a one example that we are all using in our homes. It's a cooktop burner. I will show you some experimental results from the Samuels and et al. Paper. And it's the most recent and valid paper about this topic. First, I would like to start with the ignition time. The ignition time of our cooktop burners should be within 4 seconds for the safety reasons. And this time decreases with hydrogen addition. As you can see from the figure, with the addition of the hydrogen, the ignition time decreases up to 20% hydrogen addition by volume. And it's okay, it's good for the safety limit. Let me continue with the temperature increase. And as you can see from the figure, with the addition of the hydrogen percentage, the cooktop burner temperature increases. But with addition of the 75% hydrogen, which is great, there's only like near 10% burner temperature increase, which is accepted as an acceptable limit at these burners. But how about the flashback? As I told you before, the flashback is really important phenomena for these applications, since the hydrogen property is much different than the natural gas while burning. So I can show you flashback as in the left figure. It's a stabilized flame cone that we all know. And in the right figure, the flame starts to propagate inside the tube. This happens when the laminar flame speed of the flame speed at the direction of the unburned gases is greater than the gases. So the flame front wants to go inside to the tube. And when it started, it's really problematic because the flame goes into the tube and the flame extinguish, or it can lead to big detonation problems. So we don't want that. We need to investigate flashback deeply in our studies. So here's a picture in the Samuels and et al.'s work. And they investigated the flashback at the cooktop burner, and they came up as the 20% hydrogen addition by volume results of flashback at the ignition instance. In the last pictures, I show you that the 75% hydrogen addition, but I'm now talking about the ignition, and this should be our safe limit, because after 20%, the flashback happens, and we don't want it. So in the figure, you can see that at 0.14 second, the flame front is occurred, and after that, the flame starts to propagate inside the pipeline, as you can see in the figure. And in the last figure, there is no flame at all. So what are we doing in Middle East Technical University? I would like to mention a little bit about that. For now, we calculated the laminar speed of the methane air mixtures at different equivalence ratios and also at the different pressures and temperatures. Now we are doing a numerical modeling for a simple Bunsen burner case, and we are start to build our experimental setup in the coming days. So as a conclusion, blending hydrogen to natural gas pipelines can be achievable, and we saw some examples of it. And Turkey needs to step forward for this technology before it's too late. And why? Because we can decrease natural gas import. And just imagine that 15% hydrogen addition. I gave you some numbers, and when you calculate that, $547.5 million can be saved each year as a gas import. And also, another important aspect, we can decrease the carbon emissions. However, for that, we need to work with the green hydrogen. So here are my references, and here's my acknowledgement. My study is benefiting from the International Fellowship for Outstanding Research Program of the TÜBİTAK. So thank you for listening to me. If you have any questions, I will be really glad to help.
Okay, Tahsin. Thank you for this presentation. Very nice work. Any question, comments so far from audience? Maybe you can raise your hand if you have any question or comment. Şener Hocam, buyurun.
That's a very good. Thank you very much for this nice presentation. One question, really, when you think of mixing hydrogen with the natural gas, as you know, there is 30% difference in their specific energy values, so per volume. So you have to increase the volume to provide the same kind of energy to anywhere. What do you think about the infrastructure of any country when you really start adding hydrogen in the liquid, hydrogen to natural gas to transfer them to the end user? Because either the amount of volume you need will be more to provide the same energy because of its specific value.
Okay, I get your
question. If I do remember correctly, it's a 30% difference. İskender Hoca might know better than that, better than beyond that.
So
Berk will reply.
But I really want to reply, but my work is mostly focuses on the problems with the combustion of the hydrogen addition to the gas line. So I really don't have an answer for you. Sorry.
İskender Hocam, maybe you might have a comment.
Yeah, transportation of this larger amount. Yeah.
Well, the idea, the initial idea everywhere, in fact, is indeed, as Berk mentioned, is to feed or inject or mix this hydrogen with natural gas and then use the natural gas distribution, transport and distribution infrastructure to both, in fact, to store in some way and then to transport to the end user place. So in that sense, there is no real problem of volume or whatever. Then we shall use this. The idea is this. On the other hand, you are right. Volume-wise, the heating power of hydrogen is less than natural gas, but of course, in mass-wise, it is much higher. And also, as Berk mentioned, this hydrogen burns much better with a higher, burning rate, let's say, and also provides higher energy, higher temperature. So when you do all these optimizations, you don't really use much higher hydrogen or mixed fuel than the pure methane. But the problems are, as Berk mentioned, the safety problem, and this is why we are limited. In one sense, it is a good thing. So it is achievable. I mean, in terms of volumes that we should, then we are limited. We have a long way to go to 100%. And the other problem that Berk didn't mention, but is that hydrogen is a funny species. You know, it can go inside the metals and things like that. So embrittle the metal, the pipes. So there are also some
corrosion problems.
That's correct, corrosion and other things. So it is, we should handle with great care the hydrogen business if we want to have it really usable for the general public. You know, as we mentioned, up to now, hydrogen is used massively, but by at least higher technicians or engineers, not at home. So this is the step that we have to have safely.
Okay.
Thank you.
Berk, let me ask one question. I mean, I'm always looking at the economic side. Okay. You have said that, you know, we can save like $500 million natural gas. Okay, that's good. But there is also a generation cost for hydrogen, right? It is not free. So you have to somehow generate it, and you have to pay some cost. You have to transmit that. You have to have a plant capital cost. And do you think the cost of getting hydrogen is less than the natural gas?
Actually, for now, for the green hydrogen, I don't think so. But at least we are not importing any natural gas from outside, and we can generate it in our own country.
Just perhaps to add some more. Today, in average, green hydrogen generation cost, let's say in Europe, for example, is around €9 per kilogram, whereas the gray hydrogen is around 2 or 3 or whatever, depending. So there is a gap. Of course, this green hydrogen cost will decrease with the market take-up, let's say, when we shall really use it by doing that, etc. And also, the only capital cost will be, let's say, essentially electrolyzers, okay, that we don't have for the moment. We have them, but we have them at a low capacity. We need electrolyzers about 20 megawatt. And then, well, we can consider that water is somehow free, not free, but of course, not as costly as natural gas. And the renewable electricities, as you know, Şener Hoca knows, and you all know, it's just getting lower and lower, and especially what we call the excess electricity. You know, sometimes essentially wind guys, they just sell it at negative prices. So the OPEX, as you say in your, will be much lower than compared to the this gray hydrogen. This is the hope, in fact, than to make it equilibrium. Again, okay. And the last thing, carbon price will increase. So carbon penalty will increase. And again, as we said for the glass industry just before,
then they will match, the cost will match eventually, or maybe it will be cheaper.
Yeah, well, I mean, kind of equilibrium, which will, and also with these penalties, these regulations, which will render impossible to use other kind of systems or gray hydrogen, then we should be ready to explore these ways, not only in Turkey, but everywhere, of course.
İskender Hocam, the water is more expensive than oil now.
Well, this is one way of putting it, but Berk said, you know, in Turkish, we can say hidrojen külünden doğuyor. Just combust it, you have water. Use the fuel cell, you have the water, and then you electrolyze this water. So at least
salt water.
Yeah, exactly.
Okay.
This is should be manageable.
Okay, if there is no other question, comment, we can proceed to the next one.
Go ahead.
Okay. Any question? No, thank you, Berk.
You're welcome, thank you.
The next one is Simge, Sertgümeç, a sustainable approach, use of municipal solid waste, incineration, ashes in production of concrete. Please introduce yourself.
Good afternoon, ladies and gentlemen. First, I would like to thank you to organizing committee for preparing this symposium. It's a really nice pleasure to be in here. Actually, we are going to talk about a different perspective today to energy sector. We are going to talk about a sustainable approach, actually, the use of municipal solid waste incineration ashes in production of concrete in perspective of zero waste concept. Before I move on to my presentation, I would like to introduce myself. I'm Simge Sertgümeç from İstanbul Technical University, and my basic research areas are bioenergy, circular economy, waste management, and anaerobic digestion. Firstly, I'm going to talk about the waste production and management of our wastes, and then incineration plants and the energy production. Then I will talk about circular economic models and concrete production, and we will have a final statement. So let's start with the population growth, because as all of you know, it is a very important topic. In worldwide, we are growing really rapidly. And as global scale in Turkey, also we are increasing rapidly. For example, in this figure, we took from Turkish Statistical Institute from 2010 to right now, the population was 73.7 million, and now we have 83.2 million people living in Turkey. And actually, in 10 years, we had a really big difference in population. And this population growth brings some difference in economic and social life. And these economic and social changes actually coming up with the with waste generation. And as our population grows, our waste generation is increasing also, and we have lots of different kinds of wastes, like hazardous wastes, hospital wastes, waste waters, solid wastes. And for now, we are actually creating so much solid wastes, especially in crowded cities in our country, like Istanbul, İzmir, and Ankara. As I explain, for example, I'm giving an example from Istanbul. We are creating per day, per person, average 1 kilogram solid wastes, and we should at some point manage these wastes. So how we are managing these wastes in our country is basically we are sending these wastes, solid wastes, to the landfill areas. Actually, we have 2 different landfill areas right now in our country, and we are composting them. Also, we have recovery facilities, as you know. Kömürcüoda and Seymen are the landfill areas we are using right now in Istanbul. Seymen is located in the Europe side of Istanbul city, and Kömürcüoda is located in the Asia side of Istanbul city. And we have also a capacity of municipal solid wastes that is going through these landfill areas as 19,000 tons per day, which is a really huge number, as you know. And at this point, we should talk about the waste management, but we are focusing on the integrated solid waste management in all around the world. And one of them is waste to energy concept. And we can convert wastes into new forms like electricity, heat, and transport fuels. Like we can give example to transport fuels as diesel. So as I said before, we have really wide range of wastes, and we can give some examples as solid ones, liquid ones, and gaseous ones to apply this waste to energy technologies. For the solid ones, we can give example as thickened sludge from treatment plants and municipal solid wastes. And also we have domestic sewage as wastewaters like liquid phase, and we have gaseous phase as refinery gases. So it is really important point in the municipal solid wastes, because in the literature we are seeing you can apply these waste to energy concepts to these municipal solid wastes easily. I mean, they are really suitable for this. So how can we done these processes? Basically, we can do incineration and anaerobic digestion and co-digestion processes. In the incineration processes, we are incinerating the wastes and we are creating electricity and energy and waste heat. And in the anaerobic digestion, we are taking wastes and we are putting them to the reactors, and we are creating an environment that has no oxygen. And we are putting also in the reactors microorganisms that can change these wastes into the biogas form. And it is the important point because we are gaining methane from the biogas and we are changing this biogas to electric form. So let's talk about the incineration plants. In the worldwide, we can give so many examples from Japan, for example, and from Europe. We have lots of countries from Europe that are applying this incineration plant technologies to their wastes. And what about in our country? Of course, we don't have right now a municipal solid waste incineration plant, but we are constructing it. Of course, we have lots of incineration plants, but basically we are incinerating with these plants generally hazardous wastes, hospital wastes like this. But that facility will be the first waste incineration and power generation facility for our country. And it is now located in the Kemerburgaz. And after it starts to incinerate wastes, it will be the Europe's largest domestic waste incineration plants. And we have a really high amount of wastes coming through. And the capacity is 3,000 tons per day, which is a really high number. So, of course, we are generating electricity. For example, for power, we are creating 78 megawatts electricity with this facility. We are going to actually produce this electricity. And that means, that number means actually 1,500,000 people can supply electricity for their domestic electric usage, and that is really nice. But of course, we are producing energy and we are creating electricity with this incineration plant. But of course, we are creating also wastes like ashes because we are incinerating something. And as you see in this image, we are taking the municipal solid wastes to the facility, and after the incineration process, we are producing bottom ash and fly ashes. As I said before, we have a capacity of 3,000 tons municipal solid waste per day, and their 15 to 20% amount of wastes is occurring actually as bottom ash, and also 5% occurring as fly ash. So we should manage them, and the municipality is planning to manage these ashes with landing them. Like they are planning to send these ashes with 60 to 70 transportation vehicles to the landfill sites again. And in our approach, we are thinking to make this ashes as raw materials. So I will just talk about a little bit construction sector in our country. So we have to firstly know what is puzolan. Puzolan is puzzolans are not hydraulically binding substances, and that forms compounds with a binding structure by combining with calcium hydroxide. And of course, these puzzolans in normal temperature environments with sufficient moisture, and they can be natural and artificial. So as I said before, we have bottom ash and fly ash. These municipal solid waste incineration ashes can be artificial puzzolans. Normally, in the production of concrete, we are using sand, but instead of using the sand, we can use municipal solid waste ashes. It is stated in the literature. And in this way, we can cause less harm to the nature actually, and we can adopt circular economic model and zero-based approach. So in Turkey, right now, all we know, last 2 years, we didn't have that much construction stuff because the sector was a little bit bad. But the use of concrete in the construction sector in our country is quite common. And especially in 2017, we had a rapid increase in ready-mixed concrete production. And the amount was actually really high, like 115 million meter cube. And as you know, and all of us know that with the concrete production, we are releasing so many carbon dioxide emissions to the atmosphere actually, and it causes an environmental damage because it is actually making climate change. And also in this sector, energy consumption is really high. So our final statement in this study is, if we use these fly ashes and bottom ashes coming from the municipal solid waste incineration plants, after the stabilization step, we can use them as a raw material in the construction sector. That's why we are supporting this idea so much in the circular economic model. And here is our references, and thank you for listening. If you have any questions, I can answer.
Teşekkürler Simge. So, questions, comments?
Yeah, maybe I'd like to ask a question to Simge then. So, what is it to do with the sustainability? I mean, you said you're going to be protecting the environment and you just use the ashes to make concrete.
Mm-hmm.
So what is it, why is it so useful method to protect the environment then?
To perspective of protecting environment, if you are creating concrete in a normal way, you are using sand and you are using so many energy for this sector. And if you use the ashes instead of using sand, you can firstly create value for the circular economy, because in other ways, you are just sending these wastes that are coming from the incineration plants, sending them to the landfill site. But if you use them as a raw material in concrete production, you can cause less harm to the environment. You can cause less carbon dioxide emissions to the atmosphere.
But it saves some material maybe, not the energy. Huh? Is there any difference in energy usage in both methods?
Actually, it is, but we are, the new facility will be done in 2021 April, end of March and April, so we can take the samples from ashes, but right now we don't have any incineration plant going on. So we are planning to do some research with these samples in lab scale. For further studies, we are planning to make a feasibility study actually.
And I also didn't understand why they are building an incineration plant instead of landfill gas. In Ankara, for example, the municipal wastes are turning into electricity, first gas, and then they use the gas to generate electricity. So it's a much better method than incineration. Why did they pick that method? I didn't understand that.
Yes, because we have targets, as you know, the Europe put some targets like biodegradable wastes should be decreased if they are going to the landfill sites. And also we know this, we had actually 3 landfill sites in Istanbul. Kömürcüoda, Seyment, and Odayeri landfills. Odayeri landfill was closed in 2008 because the capacity was fulfilled. And right now we have Kömürcüoda and Seyment, but they are still taking this municipal solid wastes. So our capacity is getting smaller. That's why actually they are planning to put a plant, and they start to.
Well, no, what I'm trying to say is the wastes of Turkey is different from an average European country. In average European country, they are mostly cans and glasses and papers, but the waste is mostly composed of organic matter, so vegetables and fruits and etc. So our waste is much more suitable for the landfill gas than the incineration. You know why? That's the reason why I'm asking that.
But I understand you. But right now we have landfill sites. Then you are saying just put a new landfill sites. Did I understand?
They just produce gas from that, and they use that gas to generate electricity. In Mamak, for example, in Ankara, Mamak works this way.
Methanation, he means, you know, biogas generation.
They generate some methanes, biogenic degradation, biochemical degradation, and they produce some gas. Okay.
I understand what. Okay.
Well, yeah, in France, for example, the incinerators are popular or were popular, but there are more and more let's say opposition. Simge, probably you looked at what are the emissions from these incinerators, then they are very, very strictly controlled, especially in terms of heavy metals, etc. I hope that they are planning these kind of things. And to use the ashes in the concrete generation, then you have to discuss with the cement plants, or better the, you know, the Turkish Çimentocular Birliği, Müstahsilleri Birliği, because the introduction of ash type material into the cement first and then concrete is very, very much regulated. You cannot put anything. Then your ash composition should be in a given composition, let's say. Then you have to indeed know this composition acceptable.
Yes,
then
you're right.
When you will have ashes, you will.
You are right. That is actually an approach study, and we are planning to do lab scale studies in further studies.
Mm-hmm.
We have lots of examples in the abroad to convert this municipal solid waste ashes into concrete, and it's gone very well. So we are planning to make lab scale studies in further studies.
Yes, but as Volkan Hoca said, Turkish waste is not the same waste. So be careful with that.
Yeah, that's why we are actually planning to do lab scale to see what is happening.
Can I?
Yes, go ahead, Şener Hoca.
Well, probably, Simge, you know, there are some exercise in power station in Muğla region. They use ashes of power stations in the cement industry. But at one stage, I remember clearly that you were in touch with them.
No, in Turkey, we are using ashes in concrete production, but we are using these ashes that's coming from the thermic centrals. They are doing this, but I am talking about the municipal solid waste incineration ashes. That is going to be the first.
Yeah, this is what Professor Optik is saying. Indeed.
At the end, I will come to the same point with İskender.
Yeah.
Okay.
The problem is really there was some discussion at that time. There were some radioactive materials.
Your connection is not so good. Yeah, please.
Okay.
Can you hear me now?
Yes.
Yes.
Okay. I remember the discussion at the time. There were some radioactive contamination in the ashes of power stations, and it was a problem. Do you have any experiences or discussions on municipal ashes produced
for the municipal
incineration? Do you have those problems?
Yes. I know that
you know what sort of contaminations you've got.
Yes, I know. In the municipal solid wastes, we know that we have metals, and in this image, you can see we are taking here, for example, from the bottom issues, we have metal and materials recovery generally, but I have not heard about the radioactive wastes. I mean, radioactive materials coming from the municipal solid wastes.
Yeah, this problem is kind of specific to coal, you know,
Yes.
General coal, some places, and indeed for Yatan, coal, etc., there is, it seems, some radioactivity, but I don't think that the municipal waste carries
Yes.
any radioactivity. It carries other bad things, but
Yes.
Well, as a matter of fact, coal do not have very much radioactive minerals in it, but the clay has a lot because they are smaller than 5 micron or smaller, and the clay is associated with coal deposits in most cases. So clay is the, you know, a sedimentary rock which has the highest amount of radioactives in it. So the municipals is expected to have less radioactive than the coal, probably.
Yes.
Simge, thank you very much. Nice presentation.
You are welcome.
Yeah, Ahmet Hoca, perhaps you continue. With
I mean, you ask every question, but I think right now it's okay. Thank you, Simge. Maybe we can proceed to the next one. And also this is Emre Öncü, İskender Hocam. The potential for lignite gasification and syngas electricity production in Turkey. Emre, introduce yourself and proceed, please.
Okay. Thank you. Hello, everyone. My name is Emre Öncü. I'm sharing the screen. I want to say that I am honored to be a part of this conference. My name is Emre Öncü. I am a graduate student in the Mechanical Engineering Department of Middle East Technical University under the advisory of Professor İskender Gökalp. Today, I am going to present to you our project on the potential for lignite gasification and syngas generates electricity production in Turkey. My presentation will be composed of these 3 parts. Firstly, I will try to explain the potential for lignite gasification for Turkey. After that, I will present the numerical and experimental progresses made in the project. Due to its relatively low cost, lignite, also known as low-rank coal or brown coal, has a vital position in the energy mixes of numerous countries worldwide. In Turkey, the use of lignite in the energy mix is 10.5% of the total energy generation in 2020. As we can see in the figure, lignite coal reserves are plentiful and spread more or less uniformly throughout Turkey. Total usable amount of lignite coal reserves in Turkey is 15 billion tons. However, power plants using lignite as fuel have some unfavorable characteristics and limitations on performances, mainly due to the very high water concentration of this type of coal. In addition, lignites also have high ash content. For example, according to the paper Economical Characteristics of Coals in Soma Danish region, the moisture content of lignite found in the region is between 12 and 21%, and the average ash content of the coal is 34%. Furthermore, lignite coal has highest sulfur content and lowest calorific value compared to other coal types. However, this does not make it impossible to use lignite coals in energy production. This brings us to syngas. Syngas or synthesis gas is a fuel gas mixture consisting primarily of hydrogen, carbon monoxide, and very often some carbon dioxide. Syngas is usually a product of coal gasification, and the main application is electricity generation. Syngas is combustible and can be used as a fuel. Historically, syngas has been used as a replacement for gasoline when the gasoline supply has been limited. With a previous project, it was proven that the most suitable gasification technology is fluidized bed gasification. Additionally, with the EU Optimash project with several European partners, including Türkiye Kömür İşletmeleri, one such gasification plant suitable for Turkish and Indian coals have been designed, built, and is operational today in India. This gasification plant works under 10 bars of pressure and has a power of 1 megawatts, and here we see a picture of the plant. The idea of producing syngas through lignite gasification using already available technology is economically very valuable for Turkey, namely gasifying lignite for various uses such as substituting natural gas for combined heat and power generation in gas turbines, or as a raw material for chemical industry, for example, methanol production. This project aims to assess the feasibility of using syngas generated by lignite gasification in gas turbines for combined heat and power generation in Turkey. In the picture, we see the Kemper County Integrated Gasification Combined Cycle Power Plant, which uses syngas gasified from lignite coal to produce electricity. Another significant advantage of syngas electricity generation is that this process is much more environmentally friendly than burning coal directly in conventional power plants. This advantage of syngas makes it valuable for countries other than Turkey as well. Syngas is eco-friendly because of its high hydrogen content and the fact that the carbon content of syngas can be lowered with processes after the gasification process. Turkey started investing in gas turbines about 20 years ago. However, today a significant number of these turbines are offline due to the changing energy policies. An example of these unused gas turbine power plants is the Aliağa EÜH combined cycle power plant, which our project focuses on as a technology demonstrator. Here we see a picture of the combined cycle power plant in İzmir Aliağa. Here we see a picture of one of the gas turbines in Aliağa power plant. Gas turbines were installed in the Aliağa EÜH power plant 20 years ago, while Turkey was investing in this technology. The turbines have been sitting inactive for many years because of their low efficiencies and because rising fuel prices have made them economically disadvantageous. This, combined with the fact that most of the fossil fuel consumed in Turkey is exported from other countries, shifted the investments away from these technologies and caused many power plants like the one in Aliağa to go inactive. This project aims to make these inactive power plants economically viable to operate again and reduce Turkey's fuel import spending. Here also we see a picture of one of the combustion chambers of the gas turbines in Aliağa. These combustion chambers are of the can-annular type and are designed to burn natural gas. Also, interesting to note that these chambers were once modified to burn natural gas, while the previous combustion chambers were designed to burn gasoline. Initial phase of the project involves acquiring the gas turbine technology in Turkey. This is being done by converting existing gas turbine combustion chambers optimized for natural gas to burn syngas and its blends with natural gas. Arrangements with partners are made to use a typical gas turbine combustion chamber in this fuel conversion study. The combustion chambers in the gas turbines of the Aliağa power plant is being analyzed and modified to burn syngas. Here we see the technical drawing of the combustion chamber. This part of the study includes both numerical simulation of syngas combustion under gas turbine conditions and testing the syngas combustion performances in the modified combustion chamber. This study additionally allows to define the ideal syngas composition in terms of the H2CO ratio for gas turbine burning, both as pure syngas and blended with natural gas at different proportions. This information is used to optimize the design of the lignite gasification reactors in order to approach this ideal syngas composition. For the experimental part of the project, progress is being made in two areas. Firstly, there is currently an experimental setup being constructed in Bidirectional to be used in this experiment. The experiment will involve high-pressure oxygenated flow through the combustion chamber to imitate the working conditions in a gas turbine. The gas will be heated via combustion prior to combustion chamber analyzed, and the oxygen will be added to make the hot, high-pressure gas suitable for combustion. The numerical part of the project is currently being developed. The open source computational fluid dynamics code OpenFOAM is being used for simulating the flames inside the modified combustion chamber. Another crucial development in the numerical part of the project is the collaboration with Bidirectional in the numerical studies. Thus, for experimental and numerical reasons, the combustion chambers are planned to be shipped from İzmir Aliağa to Ankara TÜBİTAK-SAGE facilities. Furthermore, the researchers in the project are advancing in the areas of pre-processing, processing, and post-processing to advance in both the experimental and numerical field of study. An innovative swirl burner for hydrogen-containing mixtures is already being studied numerically and is planned to be studied experimentally in the new combustion lab. This finally brings us to the new combustion lab planned to be built. Some parts of the mechanical engineering department of Middle East Technical University is being demolished to construct new laboratories for combustion experiments, such as the swirl burner I mentioned. And this is my acknowledgement. Thank you for listening. If you have any questions, I can answer them.
Thank you for the presentation, Emre. Let me ask first audience, any question, comment?
Yeah, this was the fourth paper from the same department under the supervision of İskender Gökalp. So this maybe gives us a chance to make a conclusion on this. The coming of İskender to Middle East, just changed many things, just we can easily see this from the quality of these four papers. And I am sure that İskender Hoca's presence there will contribute especially the combustion studies of the mechanical engineering department of the Middle East Technical University. We are also proud of having him in our advisory committee of the center. So I really want to thank all of you, and specifically the İskender Hoca, for contributing this conference, so making so great contributions to this conference. Thank you again.
Okay, thank you, İskender Hocam. Emre, don't go anywhere. I will ask some question. I mean, this is a good presentation, okay, but as always, I am looking at the economic side. So how do you do, assuming Aliya, and you got syngas from a lignite power plant, how do you going to transport to the Aliya first? How it will be the economics of, how do you want, what will be the cost of converting, of having the syngas? And is it going to be cheaper than the natural gas? Have you considered this once?
Okay, as far as I know, as far as we talked about it, the Aliya power plant is chosen only as a technology demonstrator. Another gas turbine power plant will be constructed near Afshin, Elbistan, as the project progresses. So Aliya power plant is only a technology demonstrator. It's not meant to be economically viable.
Okay, then they're going.
Ahmet
Okay.
Hoca, if you want, I can complete, but he's right. He rightly answered Emre. Indeed, as you know, all the largest reserve of lignite in Turkey is Afshin Elbistan region. Then the idea here, of course, this is a kind of, pre-project or the feasibility and demonstration type of project. The idea is to use the, not really, in fact, the facility at Aliya, but the combustion chambers and the turbine, which is inactive there, and to profit from this occasion to get some experience on gas turbine combustors, modify them, and make them usable for syngas, and as Emre rightly mentioned, to optimize also the syngas needed for these combustors, and then to optimize the lignite gasifier to produce this type of this gas composition, let's say. And then next steps hopefully would be to build the kind of demonstrator size, close to commercial size gasifier at Afshin Elbistan, to not to whatever transport any lignite, etc. And then a second step to bring one of the existing mobile gas turbines for 25 megawatt also at EÜH, but in Istanbul, to Afshin Elbistan and try to run them with this syngas. So you're absolutely right. Then this gas should be produced where the lignite is, and then use on site.
Okay, maybe another comment. this gasification, is it going to be also a carbon capture technology for lignite? Because we cannot use lignite with this dirty carbon. This is the dirty coal. Is it going to solve this carbon problem too?
The gasification process already reduces the carbon emissions from lignite. However, carbon capture, I don't think carbon capture is planned, but it can be integrated further. It can be further planned to have a carbon capture technology as well, the gasification plant.
Okay, because I know that there's a big problem in Afshin Elbistan about the dirty, coal. There are other power plants planned to be built in coming future, and this might solve the problem over there.
Mm-hmm.
Yeah, just to complete, indeed, she rightly answered, Emre. The gasification offers the possibility of capturing the CO2. We have two methods, what we call the post-combustion capture. Then you burn the coal, and then in the chimney you try to capture the CO2, which is not easy, not cheap, etc. But this gasification, the gasification offers the possibility of pre-combustion capture and also to generate hydrogen. What does it mean? As Emre said, we generate H2 plus CO. Then we can, before combusting the syngas, we can convert CO to CO2, almost pure CO2, which is easily separable from H2, from hydrogen, and then capture it and then burn just pure hydrogen. So in that sense, there is much better possibility to capture CO2 from gasification systems rather than direct burning.
Okay, I think these are very good technologies. I mean, the papers presented here, they are very useful for the energy transition of Turkey to a more sustainable energy system. Hopefully they will be implemented in future. Thank you, Emre. If there are not any other comments or questions, we can let you go.
Thank you.
Okay.
I will say a few things and also just tell you that thank you for your nice words, and we shall hopefully do several things all together. But I need to leave as I think I told you that this period of, this Thursday is the time of my course combustion teaching also at METÜ, and all of the combustion students are listening, in fact, and they listened to our presentations. But we all need to meet on another Zoom platform to finish the course of this week. So thank you very much to all of you for this excellent organization. And as you know, we'll be in touch. And good luck for the last session, Ahmet Hoca, and all the organizers. Thank you.
Okay, Volkan, thank you for this nice presentation or nice conference.
Thank you for your contributions.
Okay, thank you, everyone.
We have last and fourth session, and we will be here at 4:15. And I would like to thank to the dear moderators, dear professors, and the presenters. It was really great session as well. And yeah, see you at fourth session.
Okay.
Bye.
Bye-bye.